having discussed some of the characteristic features of enzymes in the light of their chemical nature, today we will discuss the functional nature of the enzymes. And as most of you are familiar, catalysis is a universal property of enzymes. The essential characteristic of a catalyst is to accelerate the rate of a reaction that it is supposed to catalyze, but in the process it is not used up in itself, and in an ideal situation it must be possible to recover the catalyst at the end of the reaction. As a biocatalyst in the living systems, two very significant characteristic properties of enzymes are noted, that is the catalytic efficiency. As you will notice as we go further that the enzymes provide a much more efficient catalytic system than their chemical counterparts, and there are basic intrinsic mechanisms and the conformation or the chemical nature of the enzymes is the responsible factor for providing the catalytic efficiency. We will look into that what are the basic factors that provide the catalytic efficiency. When I say catalytic efficiency, I normally mean the magnitude by which it is able to increase the rate of reaction compared to an uncatalyzed reaction, or the turnover number of the enzyme, that means number of moles of substrate converted to product per unit time per mole of the enzyme, per mole of the catalyst. The other feature which is very important is the specificity, which is again not attributed to chemical catalysts, and the enzymes provide a very specific catalytic system, specific to the extent of able to recognize the even the isomers they can distinguish, and therefore, it will be interesting to note that how do they catalyze the reaction such that these properties are built in the system. Now, another feature which I think must be important to note, that an enzyme like any other chemical catalyst does not influence the thermodynamic status of the reaction. That means, whether it is the free energy change or the equilibrium constant of the reaction, it remains unaltered during the process. It only accelerates the reaction rate by a order of magnitude. Now, just as an example, if you look at isomerization of glucose to fructose, the reaction can be catalyzed by an alkali, say NaOH. You can get isomerization. You can also carry out isomerization by enzymatic route using a glucose isomerase. In both the cases, the equilibrium constant of the reaction is approximately equal to 1. So, whether you carry out the reaction by alkali or by the presence of glucose isomerase, the reaction will end up under equilibrium conditions at a equimolar mixture of glucose and fructose, and that remains unchanged. The only difference lies by virtue of the presence of a catalyst or an enzyme in this case will be that you can reach to the equilibrium status much faster than in the case of an uncatalyzed reaction. Besides the equilibrium conversion or the equilibrium constant of the reaction, the catalysis or the enzyme catalysis also follows all thermodynamic concepts that are applied to chemical reactions also. Now, basically sometimes it may look in the case of living systems that certain reactions that are catalyzed are in a totality have a positive free energy change. A very just to illustrate my point, an example could be cited of conversion of carboxylation of acetyl coenzyme A to malonyl coenzyme A. An enzyme carboxylase which catalyzes the reaction has a free energy change of plus 4.5 kilocalories per mole. Obviously, the reaction must be non-spontaneous, should not take place as per the normal thermodynamic concepts, but we all know that this conversion does take place in the living cells. Now, the basic philosophy is which essentially or apparently it may look as if enzyme is doing something which is not allowed by chemical thermodynamics, but in practice it is not so, because the reaction is catalyzed in association with another hydrolytic reaction which is energy yielding, which has a much higher negative free energy change, and that is hydrolysis of ATP to ADP and inorganic phosphate, and the free energy change of this is highly negative, minus 8.9 kilocalories per mole. Now, essentially while the reaction takes place as a coupled reaction of the two system, the net reaction is a coupled reaction where the acetyl coenzyme A carboxylation is coupled to hydrolysis of ATP. But in practice the reaction does take place in a living cell as shown in the second half, that is the enzyme which uses biotin as a cofactor activates the carbon dioxide at the expense of energy of the hydrolysis of ATP, and you get activated carbon dioxide with a negative free energy change, which is a spontaneous reaction, and this activated carbon dioxide then carboxylates the acetyl coenzyme A to malonyl coenzyme A, and enzyme along with the cofactor biotin is released free. The second reaction is also a negative free energy change, and therefore, it also carries out, and the net reaction is sum total of the two reactions what we have shown here. So, therefore, the another feature is that the enzymes often show certain behavior which can be explained on the basis of coupling of more than one enzyme reactions, whereby they are able to produce certain net results which may look apparently to be non feasible, but otherwise they follow all the laws of chemical reaction kinetics as well as thermodynamics. Now, the catalytic behavior of enzymes can be probably best illustrated by chemical reaction rate theory. One of the most accepted theoretical interpretation of chemical catalysis can be considered from the point of view of chemical reaction rate theory, which illustrates that molecules can react only if they come in contact with each other. Therefore, that means the molecules do undergo certain collisions. Therefore, for different molecules or reactants to react, collision must take place. So, any factor or any parameter which increases the frequency of this collision between the molecule will tend to increase the rate of reaction. Now, two of the most sought after parameters, one is temperature. We know that if you increase the temperature of a reaction system, the frequency of collision will increase and thereby the rate of reaction. Another is if you increase the reactant concentration, again there also the frequency of collision will increase and therefore, the rate of reaction will also increase. However, while collision among the molecules might lead to product formation as per this chemical reaction rate theory, but it is also understood by virtue of some of the studies on the distribution of molecules which undergo reaction, that not all the molecules that collide will result into the product. It is only certain molecules which have sufficient energy to undergo a reaction will result into the product formation, and it will be only a fraction of the total molecules that are produced, that participate in the collision process are able to yield the product. And therefore, now if you consider say for example, two molecules in a binary reaction, biomolecular reaction, that is your A and B, and both of them are in the ground state, keeping in view all their electronic, vibrational and rotational ground state, but possess translational energy which makes them to move for the collision to take place. If they are to react, when they collide, the rearrangement of the electronic conformation in each molecule must take place. That you see, when you consider two molecules, say for example A and B, which are supposed to react in the presence of a catalyst or without a catalyst, if the reaction has to take place, then they must start colliding with each other. Now, initially they will be at a ground state of their electronic, vibrational and rotational ground states, and ultimately, but they will possess the translational energy because of which can make them to move and collide. And now, when they can react, they can only react when the rearrangement of the electronic distribution in each molecule, perhaps by transfer of atoms from one molecule to the other, takes place. I mean, I will just like to illustrate as probably very clearly pointed out by Eyring in his transition state theory, that every chemical reaction proceeds via a formation of the unstable intermediate between reactants and the products. Say for example, you see, take the example of a hydrolysis of an ester, a very common reaction even occurring in the case of enzymatic reactions. Now, the ester, to the ester molecule a water molecule is added. Now, this addition of water molecule results into a unstable transition state compound which have partial bonds, partial negative and positive charges at the molecule, and now this unstable molecule which has a much higher free energy than the reactants will undergo to break down and give you the corresponding acid and the alcohol. So, basically the basic philosophy behind Eyring's transition state theory states that for each reaction to occur, it must pass through a transition state which is essentially a unstable state of the molecules, or in unstable state somewhere in between the reactants and the products, and which has much higher energy than possessed by the reactants at the ground state. Now, this energy requirement is essentially considered as the energy of activation. That means, the energy of activation required, the energy required, free energy required for the reactants to reach to the level of transition state compound, compound is considered as the energy of activation, and now which will ultimately break down to give you the product, or in other word, this energy of activation acts as a barrier between the reaction to take place. I mean, unless the substrate reactant molecules reach to that, cross that barrier, they cannot get converted into the product. Or to illustrate my point further from an energy diagram, if you consider the first stage, an uncatalyzed reaction. In the case of this reaction, you see the reactants are at a ground state. Now, the x axis denotes the extent of reaction, the y state is the energy content, and then the molecules have to undergo a increase in energy till the point where a transition state is reached, and this transition state will then break down, will undergo the reduction in energy and lead to the products. These are reactants, these are products, or A and B, and this is the product. Now, this difference between the ground state and then this, the maximum level of energy at which the transition state is generated, is called as energy of activation. Now, essentially if you look at on the other part, from the energy content of the system, the energy content of the molecules in a system will essentially will show you a Gaussian distribution. That means, energy content per molecule and the number of molecules in a system will have a Gaussian distribution, and only those molecules that possess sufficient energy, which are sorted here by a shaded portion, only that fraction of the molecules will undergo the chemical transformation. That means, the transition state will be able to result into breakdown and form the products. Rest of the molecules which have much lower energy content will not be able to lead to product formation. On the other hand, when we consider the second area where we use a catalyst, the main role of a catalyst, as we will also further confirm, is to reduce this energy of activation by some means. Of course, whether it is chemical catalysis or enzymatic catalysis, the primary function or the primary route by which a catalyst functions is by reduction in this activation energy. And if you see that when the energy of activation from here it is reduced to this level, you notice that the number of molecules, the fraction of the total number of molecules has increased, which possess the sufficient energy for the transition state molecule to break down into product takes place, and large number of molecules can then take part in the reaction and result ultimately into the product. So, in conclusion, by lowering the energy of activation for the reaction, a catalyst makes it possible for substrate molecules with a smaller internal energies to react. Even at a smaller internal energy level, the product formation can take place, and that is where in fact the shaded portion, if you see the relative concentration of the shaded portion in the two cases without the catalyst and in the presence of catalyst, that will illustrate the point. Here it is the low energy of activation as a result of catalyst presence. This is indicates the high energy of activation in the absence of any catalyst. Now, the formation of transition state, if we slightly look into little more deeper into the transition state, the formation of transition state can be described and very easily studied as an ordinary chemical equilibrium process. As I mentioned earlier that the reactant molecule have to pass through a transition state, and if you can consider that the formation of transition state starting from A and B can be considered simply as a simple chemical equilibrium process. That means A and B combining to give you a activated complex AB star, where and with a equilibrium constant of K equilibrium, or you can put it say K star. Now, this K star essentially equal to concentration of AB star divided by A, concentration of A into concentration of B, or in other words your concentration of AB star at any given time will be equal to K star A into B, by simply by the treatment of the whole process as a process of chemical equilibrium. Also, this chemical equilibrium will also follow the other relationships, that is your energy of activation which is required, the free energy of activation in the process of this, in this whole process can also be given by minus RT ln K equilibrium. Let us say second equation. Now, rate of reaction between A and B, minded that we have not undergone the whole process reaction, we have only come to the transition state complex, and the rate of reaction will depend upon the concentration of AB star. The rate of reaction will essentially, larger this concentration of the transition state complex, the higher will be the rate of reaction, and this rate will depend upon the frequency at which the activated complex will decompose, and this rate of decomposition will essentially depend upon the vibrational frequency of the bond that is breaking. Now, obviously from the transition state some bonds have to break, some has to form. Ultimately the transition state complex is somewhere intermediate between the reactant and the product. Some bonds are partially formed, they will be completely formed, some bonds are still in the formation stage, and therefore the vibrational frequency of the bond that is breaking will determine the rate of the reaction at which they react. Now, this frequency you can arrive at from the theoretical treatment from two routes, by quantum mechanics as well as from classical mechanics. Now, you can see that by quantum from the if you just consider the frequency of energy of excited oscillator, from by quantum mechanics you get E is equal to h nu, and the classical mechanics also you get E is equal to k T. H is the Planck's constant, E is the energy, of course, the nu is the frequency. Similarly, here the K is the Boltzmann constant and T is the absolute temperature, and therefore, nu can be k T upon H, which is equal to, if you write again for K your R upon N, R T upon N H. You are familiar with all these terms, that is R is the gas constant, T is the absolute temperature, N is the Avogadro's number, and H is the Planck's constant. So, basically the frequency at which a transition state complex bonds will break will be determined by these factors, which can be obtained by equating the energy of an oscillator by two treatment. We had as we mentioned earlier, the rate of the reaction, if I consider as R, will be equal to nu A B star. Third, the rate of reaction will depend upon the concentration of the transition state complex, and the frequency of this breakdown of this transition state complex will be same as that of the frequency of. Now, that can be written as R T over N H into K star into A into B, the expression we got for the concentration of the transition state complex from the chemical equilibrium process. So, basically you can look at now this term essentially is nothing else, if you compare with the kinetic term, the reaction kinetics is the second order rate constant. Let us say if I define K 2 as a second order rate constant for the reaction of A and B, it becomes K 2 A into B, or in other words the second order rate constant will be nothing else but R T upon N H into K star. Again you notice a significant fact here, that the rate constant is directly linked, all these are constants if the temperature is constant, obviously if the temperature is constant, these are all constants. So, basically the rate constant is dependent upon the equilibrium constant of the transition state process, the conversion of the A and B into the transition state complex, and this also gives you a relationship between the rate constant and the K star, the equilibrium constant of the formation of transition state complex. Now, obviously it will imply, or it will also be a very logical conclusion, that the faster reactions, if the reaction has to go at a very fast rate, then they must have a larger value of K star. That means, at a fast rate the reactants must go into the transition state, or they must have higher concentration of A B star. Now, this equation will also allow you to calculate the value of K star and hence the value of activation energy using your earlier equation, that is your E star is equal to minus ln RT. In fact, this should be K equilibrium can be K star here. In fact, I have written it K star. So, now if you use the equation number 6 and 2, you can calculate the value of energy of activation for a given system, and obviously again you can also conclude that the faster reactions will have a smaller value of E star.
So, is the energy of activation not equal to KT?
Pardon? No, energy of activation is not equal to KT. This is the energy of the oscillator. I mean energy term for the oscillator based on the classical mechanics. This is not energy of activation. E star is the activation energy of activation, and energy of activation can be calculated from here, and which will be related to K star and also can be related to K 2, and the two conclusions which we can make from this analysis is that, one, that the fast reactions will have a higher value of K star, equilibrium constant for the conversion of reactants into the transition state, or in other words the fast reactions will have higher concentration of A B star at equilibrium. The second is that the fast reaction will have smaller energy of activation. If you combine the 6 and 2, the energy of activation for faster reaction, if the K2 is high, will mean lower energy of activation. So, basically these two conclusions do arrive from the theory of reaction rate theory, which is now well accepted world over in the. Now, going further from that point, if you look at what we talked about Kt equal to RT over NH K star, you can also write K2 as equal to further by substituting the value from 2 RT over NH into exponential minus E star over RT 7. Now, this, as you all know, we call it a frequency factor, which is often written as A. The frequency factor A star, you can say A, because A is the reactant we are considering. So, A star exponential minus delta E over R T, which is very common expression what we all know as Arrhenius expression, and E star again, the term E star can again be separated into both enthalpic and entropic contributions. That means, your E star can be equal to delta H star minus T delta S from second law of thermodynamics. That means, the energy of activation can also be considered both in terms of entropic contribution as well as enthalpic contributions, and if you separate into it, then you can write K 2 equal to R T over N H exponential delta S star over R T delta R sorry into exponential minus delta H star over R T, and that is what gives you. So, ultimately the final conclusion is that for a catalyst or enzyme in our case, as we are talking about, to be able to increase the value of K 2, it must be able to reduce the energy of activation or increase the K star value, that is your the equilibrium constant for your. Now, that applies you commonly, this conclusion will apply commonly to a chemically catalyzed reaction or a chemically or enzymatic catalyzed reaction. Now, if you look at the performance of some of the enzymatic catalysts as compared to chemical catalysts, you will notice that enzymes provide very efficient catalyst. Now, a simple example where I can compare the reaction which can take place both by chemical catalyst as well as by enzymes is the hydrolysis of hydrogen peroxide, breakdown of hydrogen peroxide into water and oxygen, a very common reaction that takes place in living cells by the enzyme catalase. It can also be carried out by colloidal platinum. The reaction is also feasible under normal conditions without any catalyst. That means, not a very non-spontaneous reaction, it is possible to carry out. The corresponding energy of activation for this reaction without any catalyst is 18,000 calories per mole, as against in the presence of colloidal platinum as a catalyst is 11,700, and catalase for the catalase is 5,500. So, you notice that one thing, that the enzyme, and this is just a illustrative example, but I think a similar example can be cited from a variety of reactions that can be carried out both by chemical catalysis as well as by enzymatic catalysis, and the conclusions are almost same. The enzymes are able to bring down or reduce the energy of activation to a very large extent compared to chemical catalysts, and of course, we will again see how does it do. Another way to look at is another very interesting reaction in the living systems, that is on oxidation of methane. The methane monooxygenase enzyme oxidizes methane into methanol spontaneously in the living cells, particularly those organisms which can survive or consume methane as a carbon source. And this is the very first reaction which they carry out when the methane is used as a carbon source. Now, this reaction can also be carried out chemically using a chemical catalyst with a zinc catalyst at 400 degrees centigrade and high pressure, almost a few hundred atmospheres, and the turnover number is of the order of 2 into 10 to the power 4 per second. That means, number of moles of methane oxidized per second per mole of the catalyst. The same reaction if you carry out at ambient conditions 25 degrees centigrade and ambient atmospheric pressure, the turnover number is as low as 1.5 10 to the power minus 7, almost negligible. Now, in the presence of the enzyme methane monooxygenase at 25 degrees centigrade and obviously at ambient pressure, the turnover number is 2.2 into 10 to the power 3, a much higher value, although it is lower than the one which is obtained at 400 degrees and few hundred atmospheres, but compared to a ambient conditions and the same catalyst, the catalyst here also it is zinc as a catalyst, the value is much higher. Now, very often a comparison of the first and the third case is not logical, because the reaction conditions are different, and then considering and comparing the turnover number may not be a very reasonable proposition, but if you compare under the same conditions, the enzyme as a catalyst will provide you a much more efficient system, and I think one should look at how does it do that? The enzyme, how does it provide this kind of an efficiency compared to a chemical catalyst? Because as I mentioned, the ultimate goal in both the cases is the same, to reduce the energy of activation. But the enzyme is able to reduce the energy of activation to a large extent as compared to a chemical catalyst, and also its turnover number is much higher. Now let us see what happens when we consider an enzymatic catalysis. Now in the case of enzymatic catalysis, we must bear clearly in our mind that one of the characteristic features is that enzymes has certain ligand binding sites, and more specifically substrate binding sites. That means enzymes can bind to substrate, forming enzyme substrate complex. Now these enzyme substrate complex then again provide a system which will undergo the energy of activation, undergo the transition state before the product is formed. Now if we consider, let us say, an enzyme catalyzed system and an uncatalyzed system, if you consider, let us say, a E plus A plus B, the same what we were talking about, a reaction between A and B, if we consider two routes, one is E, the enzyme does not take part in the reaction, an uncatalyzed reaction, and it goes to E plus P. In the second case, we can also have that enzyme binds the substrates E, A and B and forms a enzyme substrate complex EAB. It also undergoes a transition state EAB star, and then it goes to enzyme and product. Now let us consider the rate constants is K here, Ke here. Now obviously when we are considering the lower route is catalyzed one, enzyme catalyzed, the upper route is uncatalyzed. That means essentially enzyme has no role to play here. The enzyme binds to the substrate and then undergoes transition state and then forms the product. Now in the middle case, from the enzyme and the transition state AB, you can also form the EAB activated complex. Now if you consider the equilibrium constants of all these reactions, equilibrium reactions, let us say if this is K star, this is Ks, K star E and K star S. Now thermodynamically we can notice that ultimately we are interested in this as a catalyzed reaction, we are interested in the EAB star, which is the complex transition state complex, which will give you a product at a much faster rate. Essentially I think Ke is much higher than K, the lower being a catalyzed reaction. Catalyzed reaction will have a much higher reaction rate, and so essentially to really get the reaction at a high rate, we want a larger concentration of EAB star. And now that if you look thermodynamically, this product EAB star can be obtained by either of the routes, either it can go this way and come here, it can also come this way and reach to this side. From either way, under equilibrium conditions, it is possible to arrive at this complex, and if you consider the two routes, then your Ks into Ke star, that means the left hand side route, should be equal to K star into Ks star. The equilibrium constant, multiplications of the equilibrium constant of these stages should be equal. Now we have, as I have said earlier, the Ke is greater than K, and again also K is equal to RT over NH K star. Therefore the Ke star is much greater than K star. Is that right? And therefore it will imply that Ks star, that is your Ks star, this equilibrium constant is much greater than Ks. This equilibrium constant Ks star, that means the binding of the enzyme to the AB complex, uncatalyzed AB complex, is much larger than the Ks, than the binding of the enzyme to A and B, which essentially implies that the enzyme binds AB star more tightly. The higher value of K star means the enzyme binds AB star more tightly than the substrate molecules. Essentially, the general concept that enzyme binds, yes, enzyme has certain substrate binding sites on its molecule, but conformationally it is more complementary to the enzyme, to the substrate transition state, and that was the contribution which was stated in very clear terms by Linus Pauling, that enzymes are molecules that are complementary in structure to the activated complexes of the reactants they catalyze. The attraction of the enzyme for the activated complex would thus lead to a decrease in its energy and hence decrease the energy of activation for the reaction and to an increase in the rate of reaction. Basically, the enzyme is in structure conformationally which is very much complementary to the activation or to the transition state of the substrates, and by binding that it stabilizes those transition complex. What we understand by stabilization of the transition state essentially means that the enzyme, because of its conformational complementarity with the transition state, it binds and stabilizes the transition state complex. So, at any given equilibrium the concentration of the EAB star that is the product of this binding is much higher than as if the enzyme does not take part. If suppose this enzyme was not a biocatalyst, if suppose this E would have been a chemical catalyst, this binding would have not been feasible, because there would have been no complementarity. Catalytic function might, the catalyst might be able to perform the catalytic function by any other mechanism, by acid base catalysis or covalent catalysis, which we will discuss later, but the contribution made by stabilizing the transition state of the substrate will not be possible to be provided by the chemical catalyst, which the enzyme is able to provide, and thereby it increases the stability of EAB star and thereby reduces the energy of activation and leads to the formation of the product. And that is what in fact was a very major contribution in the understanding of the enzyme functions made by Linus Pauling. Now, if you look at the yes.
So, even for a unimolecular reaction, we will have an activated complex.
Yes.
So
For the unimolecular reaction also, as I mentioned, for any reaction whether unimolecular or bimolecular, the substrate or the reactant has to undergo a transition state. It cannot, a product cannot be formed without undergoing a transition state. So, even if it is a single as a matter of fact, practically if you look at, there are hardly any reactions, very few reactions which are single molecular. See, apparently it may look, hydrolysis may be a single unimolecular reaction, but it is not so. Even in the earlier example where I discussed the hydrolysis of esters, it is the addition of water molecule to the ester which leads to transition state. So, most of the reactions essentially undergo or involve either cofactor or water molecule or excepting certain isomerases, yes, you are right, they will be truly unimolecular, but even in that case the molecule has to undergo a transition state, otherwise the reaction is not feasible according to reaction rate theory. Now, if you look at what is the contribution of the reduction, what is the magnitude of the contribution, I think yes. So, coming back to the role of the energy of activation on the reaction rate constant, you will notice that if you take arbitrary value of energy of activation, say from 25 kilocalories per mole downwards to 5 kilocalories per mole, the decrease of activation energy results in a very significant increase in the reaction rate. The magnitude, if you look at every step of reduction of the energy of activation by 5 kilocalories per mole, you will see that from starting from 3.16 to 10 to the power minus 6 at a energy of activation of 5 kilocalories per mole, you will go up to 1.33 into 10 to the power minus 10 to the power 9. That means a increase of the magnitude of by 10 to the power 15 fold of the rate constant. So, basically I mean it is a very significant energy, significant increase in the reaction rate constant, and the I mean just as a sort of a conclusion of this table, it will give that the rate of reaction under any given set of conditions, that means if you maintain same temperature and pressure and the substrate concentration, increase by a factor of 4.58 into 10 to the power 3 fold in the reaction rate constant can be achieved for every drop of 5 kilocalories per mole, which is a very large. So, therefore, even a decrease of the energy of activation by 5 kilocalories per mole can lead to an increase of the reaction rate by a factor of 4.5 into 10 to the power 3, a very significant number. And as a matter of fact, in practice, in the case of most of the enzymes, the decrease is of the order of about 15 to 20 kilocalories per mole in the case of energy of activation. So, therefore, one can achieve a very high catalytic efficiency in the case of enzymatic catalysis, and as you notice that this efficiency is primarily achieved by two distinct factors, as we saw today, which are unique compared to chemical catalysis. One is that enzymes have binding sites for the substrate molecule. The second is the enzyme conformation itself is complementary to the transition state complex, thereby it can stabilize the transition state and thereby increase the concentration of transition state in any given reaction at equilibrium, and thereby. Now, if you look at the whole picture of the enzymatic catalysis, again the energy diagram, as we notice the bold lines which go here from the starting state, from the ground state, E plus A plus B, uncatalyzed reaction, non-enzymatic reaction is this one, and you need the molecules have to reach to this status of the energy, so that the activation, the transition state can form, and it can be broken down to form the enzyme and product. In what happens in the presence of the enzyme molecule? The enzyme binds to the substrates A and B, forms EAB, and essentially this process also undergoes energy of the activation process. That means, there is some amount of energy is released by this binding, and the enzyme substrate complex, instead of starting from the level of the ground state of A and B, now has reached to a state little higher than the ground state by binding process, and from there then again it goes to a the bound state. I mean, before reaching to the binding, even the binding process will undergo the transition state, and after transition state it goes to a for this binding process EAB is the product in other case, and then from here it has to the EAB has to go to transition state EAB star, as I showed in the earlier comparative figure, and then this EAB star, which is essentially much smaller than the energy level of AB star, uncatalyzed reaction. So, basically you have an advantage, and this EAB star is reduced by virtue of the complementary nature of binding of the enzyme molecule to the AB star. Essentially the concentration of EAB star is increased by significant amount, and thereby lower energy level, at lower energy level this equilibrium can be achieved. So, basically the two factors which contribute to the reduction in the activation energy or the efficiency of the catalyst, as enzyme as a catalyst, one is binding of the substrates, other is complementarity of the enzyme molecule to that of the transition state, and therefore, and then subsequently again the same process follows on the reverse direction. That means, EAB star undergoes into breakdown products, whereby instead of product directly being formed, you form EP, the enzyme bound to the product, the enzyme product complex, and then this EP again breaks down to the next level of your product level, to the final, which is same as of the uncatalyzed reaction. Therefore, one is by binding process, the enzyme processes start at a much higher energy level than the ground state as applicable in the case of uncatalyzed reaction, and the other is the complementarity of the enzyme conformation to that of the transition state complex. These two factors put together give you a much higher catalytic efficiency, as we noted in the case of one of the examples which I illustrated, to carry out a conversion of reactants into product. And the dotted line here indicates the process. In fact, as a matter of fact, I have shown here only one step, just for the sake of clarity and removing the congestion, whereas this process might undergo more than one humps. For example, binding of E to A and then EA further binds to B in different sequences, and depending on the nature of the catalysis, and but there can be more than one processes undergoing here, and thereby the binding process can provide you a large fraction of the activated energy to be compensated during binding process and reducing the energy of activation thereby. And such a process essentially therefore leads to a very efficient catalytic system. The other part of what I mentioned into the early in my first presentation about the specificity, coming back to specificity, again the presence of ligand binding sites on the enzyme molecule are responsible for specificity. The so called ligand binding sites, and when we consider the ligand binding site along with the catalytic sites, what we consider as active sites on the molecule, they constitute for the specificity, and we will discuss that in our subsequent lectures. So today, if you recall, we have considered in general the basic theoretical consideration behind the catalysis as it applies to any chemical process. Secondly, how enzyme under the same background is able to provide much larger reduction in activation energy and provide a more efficient catalyst compared to a chemical catalyst. And with this we will stop today.